Let me okay, can you see my screen now?
Yes, we can see you. Just now start.
Okay, okay now. Okay, good morning. So this is the plan for today. And if you look at the top of the screen, so that is the theme. That is the theme bar. And there are two parts to this theme bar. On the left-hand side, that is the overall plan for this workshop. So there are 6 topics, and we have already covered 3 yesterday, and we are going to cover the remaining 2 today. And on the right-hand side, you should be able to see the sub-theme for each main theme. And so at any one time, you should be able to tell where in this overall workshop and one slide is actually in. So hopefully you won't be lost. Okay, so for today we are going to look at the neighborhood counting similarity sequence. And yesterday we have discussed neighborhood counting in general, and then we look at how to specify neighborhood counting for multivariate data. And today we are going to look at how neighborhood counting similarity can be specialized for sequence data. And later on, we move on to look at how it can be specified for graph. Okay, in the case of sequence, we are going to look at these topics. Let me move this one. We are going to cover these topics. And once again, so this is the same for all the main topics. I'm going to cover motivation, so what it is precisely, and the algorithm, because for any similarity, you have to know how to compute the similarity. And then I'm going to show an example plus some evaluation result I have done in the past, and how to generalize the basic notion of the sequence similarity to consider more complex cases. Okay, and the motivation for the sequence similarity is pretty simple, because we have a generic similarity in the first place, which is called neighborhood counting similarity, or NCS for short. And it is generic in the sense that it can be specialized for different types of data. And so, and the sequence is a main type of data, and it is quite common in various fields. And one example is the language is a good example of sequence data. And so is the DNA sequences. And there are many, many examples of sequence. So it is quite important to be able to specialize the NCS for sequence. And additionally, I also want to estimate probability for sequence data in sequence data space. Now, to specialize NCS similarity for sequence or for any data type, we need to do 2 things. So the first one is we need to define the data space precisely, and then we also need to define the neighborhood space. And then we can, we know that neighborhood counting similarity becomes a way to count your particular neighborhoods. So in the case of sequence, and the data space is defined as the set of all sequences that can be defined by a given alphabet. So we begin with an alphabet, and that is a finite set of symbols And then a sequence is simply a string of symbols taken from this alphabet. And then when you put all of these sequences together, that is the space, that is the data space. So this should be fairly straightforward. A neighborhood space. So this is a bit tricky. And so there could be different ways of defining a neighborhood space. But in my approach, what I did was I take a neighborhood as a subsequence, and then the neighborhood space becomes the set of all possible subsequences. So a subsequence, so A is a sequence as well. So a subsequence of a given sequence is simply obtained by deleting 0 or more symbols from the given sequence. You begin with one sequence and then you delete 0, 1, or any number of symbols from the given sequence, then you end up with a subsequence. And then and this subsequence can be interpreted as actually a set of sequences, and this set of sequences is defined in this way. So given a sequence S, a sequence S, and then let me see, and this is a little bit yeah. So the neighborhood given a sequence S, then one neighborhood of this sequence is a subsequence SS, and that is regarded as a set of sequences and defined in this way: a set of all sequences X such that the subsequence SS is a subsequence of X. So this definition is a little bit convoluted. So this means that you begin with a sequence on one side, and then you obtain a subsequence by deleting 0 or more symbols from the sequence. Then you end up with a subsequence. And then this subsequence should be a subsequence of many other sequences. When you put all of these many other sequences together, and that becomes part of the neighborhood, part of one neighborhood of the sequence. So as a result, a subsequence is taken as a neighborhood of a given sequence. And when you put all of these possible subsequences together, and then you obtain neighborhood space. And actually, a subsequence is a sequence. So you can say that a neighborhood space is again the space of all sequences. Now the big question is whether this neighborhood space is a sigma algebra. So you can define neighborhood space the way you like, but the important thing is you need to make sure this is a sigma algebra. So this is a requirement and for the probability to be valid. And the sigma algebra, that is simply a set of subsets from your data space. It is closed under some operations. It is closed under complement operations. It is closed under intersection. So this means so if you begin with one sequence, then you need to make sure that its complement is also part of your neighborhood. And so this is clearly the case. So you begin with an alphabet, and then a sequence should have its complement. the complement is the complement is another set of sequences that together make up the whole neighborhood space. So so it is closed under the complements, and it is also closed under the intersection. Remember, I explained earlier. So a subsequence is regarded as a set. So you have two sets, and then their intersection. So their intersection should be the intersection of the two sets of sequences. Then you end up with another set of sequences. So that is taken. That is so that should also be part of the neighborhood space. So this neighborhood space consists of sequences, and so it is closed under these two operations, complement and intersection. So it is a sigma algebra. So after that, the neighborhood counting under this interpretation of neighborhood. So counting common neighborhoods amounts to counting common subsequences, and this results in the all common subsequence similarity. So this similarity was published in this paper number 10. It is the all common subsequences. So this was published in IJCI 2007. Okay, let's move on to look at how to calculate the all common subsequent similarity. So this is a big question. So the concept is simple, and given two sequences, and to measure their similarity, and all you need to do is to check how many subsequences are common to both sequences. So conceptually, this is quite simple, but doing so is not so straightforward. And if you want to take a brute force approach, then you need to examine all possible subsequences of one sequence, and then you look at all possible subsequences of the second sequence. Then you compare whether they are identical or not. So this brute force approach is clearly exponential in the length of sequence. So that is not a viable approach. And luckily, we have a dynamic programming approach which is quite efficient. And this dynamic programming algorithm was published in the same paper as well, in the IJCI paper. So this algorithm is based on this theorem, and we have two sequences, X and Y, and they are represented in this way. So X1, 2, 3, and they are symbols from the alphabet. And so we use the notion phi of M and N to represent the number of common subsequences of X and Y. So we have introduced such a notion. And then the theorem says that this value can be calculated in one of two ways. And if this symbol is the same as the other symbol, then the phi of M and N can be calculated in this way. And so we only need to look at the previous number, that is M minus 1 and N minus 1, and then we multiply this by 2. So if this is the case, but if this is not the case, then we can calculate the phi M N in a different way. look at this one. This is the second way of calculating this number. And so again, we look at the previous value, which is the phi m minus 1 and n. But that alone is not enough. We need to look at another quantity, which is phi m and n minus 1. But this is not enough. We need to take away another quantity, which is phi n minus 1 and minus 1. So that is how we can calculate this number. So this is a recursive equation. And so to calculate this value, we need to construct a matrix. We initialize this matrix, and then we can do the calculation by walking through this matrix line by line. And in the end, we should be able to calculate this number. So this is a dynamic programming algorithm. The dynamic programming algorithm, it is efficient because it doesn't need to repeat. A lot of operations. But we do need space to store the operations that have already been completed. So for dynamic programming algorithms, you need to establish the recursive equation. So to calculate to count all common subsequences. So we have designed the dynamic programming algorithm, but we have designed another algorithm to do so, and so that is called the grid algorithm. We give it a specific name, the grid algorithm, and this algorithm was published in actually 2 papers. So this is joint work with my longtime collaborator, C.S. Elsinger. So it is initially published in this paper, but later on, so after I published the IJCI paper, the all common subsequence paper, and then the C.S. Elsinger got in touch with me, and then we teamed up with Sven Raman, and then we worked together to extend the ACS, the all common subsequence algorithm, and his grid algorithm, and we looked at all the many special cases. And then we jointly published one paper, this in Theoretical Computer Science Journal. And so the grid algorithm became matured in the second paper, in the Theoretical Computer Science paper. Some initial ideas was discussed in the first paper. Okay, the grid algorithm works in this way. So again, we have 2 sequences, but we assume that they have no repeated characters, And then we introduce this notion, so that represents the number of common distinct subsequences of a given pair of sequences. And then we introduce another notion, the phi k of x and y. So this denotes the number of k long subsequences. So k long subsequence, it means that the subsequence has k symbols in it. So that is the k long subsequence of x and y. and then we introduce a matrix E of K, and this matrix is specified in this way. So every element in this matrix denotes so the matrix is an n by n matrix, and then the elements of the matrix is defined in this way. So when k is 0, when k is 1, then the entries are defined in this way. So the elements ij is 1 if so these two symbols, if these two symbols are identical. But this Eij is 0 if they are not equal. So this is the matrix definition when K is 1. And for bigger K values, and then the elements of the matrix are defined in this way. So the Eij for K, so that can be calculated in this way. So we begin with the Eij for 1, and then on this part, so we look at the immediate earlier matrix. So this is K minus 1. So that is the earlier matrix, and then we look. So we look through its entries, A, B, but we need to make sure the entries are greater than I and J. So we need to make sure that the index A is greater than I and index B is greater than J. So we only need those entries which are actually greater than I and J. Then we put them together. We end up with a quantity. Then we multiply this quantity by this value. That will give us the values for a new matrix. And then the phi k of x and y. So that is the all k long subsequences can be calculated in this way. So we only need to look at one matrix, that is e to the power of k. So we put all the numbers in the matrix together. We add them up. So that will give us the number of all k long subsequences. But when we vary the k from 1 to infinity, then we will end up with the number of all common subsequences. So which is this one. So phi of x and y, it can be calculated by 1. So the 1 represents the empty sequence. So if we want to count empty sequence as a common subsequence, then we need to include this 1. And then we vary the k from 1 to infinity, and then so we end up with phi of x. But actually, we don't need to go to infinity because once we reach certain points, then we realize the matrices become empty, become all zeros. So there's no point in going further. So this is the great algorithm. Now I'm going to illustrate how to use the dynamic programming algorithm and the great algorithm. Now we consider two sequences, x and y. So x is like this. X is QWER and y is QAWSR. Then, according to the dynamic programming algorithm, we need to construct a matrix. And here we have, so we have 4 symbols in this sequence. We have 5 symbols in the other sequence. So as a result, we need to construct a 4 by 5. But we need to look at a special case, that is the initial case, when both sequences are empty. So we actually need to consider a 5 by 6 matrix. But you can arrange it in different ways, and I arrange it in, as a 6 by 5 matrix. We need to consider the case when the sequence is empty, because at the beginning, when we construct the sequence, at the beginning we have an empty sequence. Then we add in the symbols one at a time. So when we, at the beginning, we have no symbol, so that is 0, empty. After we add one symbol, and then we have the Q. If we add the second symbol, we have the additional W. So we have, and so this is for one sequence, and similarly for the other sequence. So the initially we have empty sequence. So we have 0 symbol, and then we add in one symbol, and then we have the Q. We have the Q. So as we add more symbols, we will have longer sequence, and eventually we have the sequence that we want. So that is the meaning of this matrix. And initially we need to initialize this matrix. So when the index is 0, then we have value of 1. So for the zero row, we initialize the matrix to 1, and for the 0th column, we also assign 1 to this column. And then all we need to do is to work out the numbers for the remaining entries of this matrix. So for this entry, so that corresponds to row 1 and column 1. So this value can be calculated by these 3 numbers, only these 3 numbers, and that are before this entry. So how to work out this value depends on this symbol and that symbol. So if they are the same, if they are equal, and then we need to double this value or multiply this value by 2, and this gives us 2, because Q is the same as Q. And now let's move to this entry. And this value is dependent on these 3 values, and we need to check whether this one is equal to this one, and clearly they are not equal. And as a result, this value can be calculated by adding these 2 values up and then take away this value according to the theorem, and that will give us 2. So this means the value for this entry is the same as the previous one. Then moving on to this one, and so that corresponds to E and Q. They are not equal, and as a result, we need to add up this value, and then we take away this value that give us 2. So we repeat this process for this value as well. So for this row, we have 2. And what about this row for these values? And they are all value 2. And that is because in this sequence we have A, but in this sequence there's no A. So we need to apply the same formula to work out these values. But let's take a look at this one. Take a look at this. And for this entry, the A is not equal to Q. So we need to calculate this value by adding this number and this number, but take away this number. That will give us 2. So it is 2 in all the entries in this row. And for this row, it is different. And for this one, it is W and Q. They are not equal, so we get the value of 2 for this entry. And W in this sequence is equal to W in the other sequence. So we need to double this value. That gives us 4. And for the remaining entries in this row, and because these 2 symbols are not equal to this one, so we simply copy the value over. And we repeat this process for all the entries until this one. So the last entry, because this symbol is equal to this symbol, so we apply one formula, which is to double this value, that give us a value of 8. So as a result, we can conclude that the number of common subsequences between this sequence and this sequence is 8. It's 8. And so you can verify whether this is the case. So you can enumerate all possible subsequences. So I can give you one example. So for these two sequences, so one and the subsequence is Q. So every symbol in this every symbol that is common would be one subsequence. So Q is a subsequence, W is a subsequence, E is not, but R is a common subsequence. So that is one length subsequence. And another subsequence is QW, and QW. So that is a subsequence. And another subsequence is the QR and QR. So that is a 2 long subsequence. And WR is another subsequence, WR and WR. That is again a 2 long subsequence. And now the question is there a 3 long subsequence? A QWR is a 3 long subsequence, QWR. So that should be all subsequences. Now, one additional subsequence is the empty subsequence. So as a result, we have 8 subsequences altogether. Okay, now, so we have illustrated the neighborhood counting, the dynamic programming algorithm for calculating ACS. Now, what about the grid algorithm? So the grid algorithm is interesting. And for the grid algorithm, we need to work out a number of matrices. So this is different to the dynamic programming algorithm. So for the dynamic programming algorithm, we only need to work on one matrix, which is this one. But for the grid algorithm, so we need to work on the number of matrices. So this is one matrix. So this is the initial one. This is the initial one, and it means that the 2 sequences are A, B, C, D, E, F. And the B, A, E, D, C, F. And then we construct a grid like this. And this is the grid. And then at the intersection, at each intersection, we need to check whether the corresponding symbols are equal or not. Look at the first grid, and the corresponding symbols are A and B. So they are not equal, so we don't draw a circle. And we don't draw anything. For this intersection, so the corresponding symbols are equal, both B. So we draw a black dot, and this black dot means that there is one long subsequence, and one long subsequence is simply B. B should be a common subsequence, and clearly that is the case because B appears in both sequences. So this is one. And for the remaining intersections, so we have no black dot, indicating that there are no one long subsequences. Now for the second line, and clearly there is a black dot here at this intersection. So that means, and so the corresponding symbols are equal. And clearly this is the case. And this black dot means there is one long subsequence at this point. And similarly, there is one here and that corresponds to E, and there is one here that corresponds to D, and there's one here that corresponds to C, and here for F. Okay, so this is the first grid. And the second grid will be built on top of it. So the grid on the right hand side is built on top of it. So we need to, so we begin with one black dot, and then all we need to do is to draw arrows from one dot to another dot, that is to the bottom right of this intersection of this dot. And clearly for this one, all of these black dots are to the right and the bottom of this black dot. So we can draw arrows from this one to this, an arrow to this, an arrow to this, an arrow to this. And we repeat this for this one as well, because all of these black dots are to the bottom right of this intersection. So we can draw arrows from this black dot to all of these. And then we need to repeat this for this black dot. And we can draw an arrow from this to this one. But we cannot draw an arrow from this to here because this one is to the top right hand, not the bottom right. So we don't draw any arrow from here, to this. And similarly for this one, we can draw an arrow from here to here, because this one is to the bottom right. And similarly, we can draw an arrow from here to here. And this give us this one, give us this. So this is the second grid, And then we can draw, so we can identify another one. So this grid give us the two long subsequences. So the first grid give us the one long subsequences, and this one give us two long subsequences. And every arrow corresponds to a two long subsequence. Now we want to identify the three long subsequences. And the 3 long subsequences can be identified in this way. So there is a 3 long subsequence in here. From here, this grid, this black dot to here and here. Okay, and then from here through this dot to here. And then from this dot to this dot and to this one. So beginning with this black dot, there should be 3 long subsequences. This is one, and this is the second one, and this is the third one. And similarly, beginning with this dot, we can identify 3 long subsequences. So one is here, from here to here and here, from here to here and then to here, from here to here to here. Okay, so from this grid, we can identify the 3 long subsequences as well. And we can, from the same grid, from this grid, we can identify the 4 long subsequences as well if we want. But in this particular example, there's no need to go any further because there's no further black dot to the right. So based on this, we can construct these matrices. So this one corresponds to the initial matrix. And for this matrix, so this is this is a 6 by 6 matrix, 6 by 6 matrix. So all cells are 0 unless except for these cells. So we have 1 in these cells. So they correspond to the black dots. And then the second matrix is worked out in this way. So there's a 4 here. So that 4 corresponds to the 2 long subsequences beginning at this cell, so at this location. So we have a 4 for this position, and we have 1 for these 3 positions. So these correspond to this one. So there are 4 arrows beginning from this intersection. So there should be a 4 in that position. And there's a 4 here. There are 4 arrows, so there should be 4 here. So there is only 1 arrow leaving this black dot. So there is a 1 here. So there is 1 arrow leaving this dot. So there is a value of 1 in that position in the matrix, and the value of 1 for this. So that is the second matrix. And the third matrix is like this. So this corresponds to what I said. So this is constructed. So this is constructed by according to this one. So that is how we calculate the values for any matrices. So you can see that we need to calculate quite a number of matrices, and then in the end we add up the numbers in every matrix, and then we add those numbers up. That will give us the total number of subsequences. So now we construct 3 matrices. So we add up these numbers. So that will give us 6. We add up these numbers. That give us 11. And then we add up these numbers that give us 5. We add them all up. So that gives us the total number of subsequences for these two sequences. So the grid algorithm is more complex than the dynamic programming because the dynamic programming algorithm, you only need one matrix. So this so the complexity of this one should be m by n. So m is the length of this, n is the length of this. So we only need so many calculations. But for the grid algorithm, we need to calculate a number of matrices. For each matrix, so we need to calculate these many operations. So we have m by n for each matrix. Then how many matrices do we need to calculate? So that could be a big number. So the grid algorithm is more complex than the dynamic programming algorithm for the same problem. Now the ACS or all common subsequences is clearly is a concept, and that is also a similarity. And we have at least two algorithms to calculate that ACS similarity. Then what about the applications? So what is the use of such a similarity? And this similarity can be used in these applications and possibly many more. And the DNA sequence classification. So DNA sequence, so that is the code of life. So sometimes we need to classify the DNA sequences. So one specific problem is, given the DNA sequence of the ACGT values, predict whether a sequence is a coding region or non-coding regions. We know that in the complete genome, not every sequence of the ACGT values code any have meaningful code. Only some segments or some regions of the genome have code for some proteins or for some organs. So we go through the whole genome sequence. We want to predict which sequence is a coding region. So that is an interesting problem. Such a sequence is a sequence of the ACGT values, and we want to make sense of it. So in such a problem, and we can use the ACS similarity, but obviously you can use others, the sequence similarity measures as well. And another application is the anomaly detection. And this is one specific problem. Given a sequence of observations, predict whether a sequence is anomalous or not. Anomalous. Say, for example, you use a program to monitor the server activities. You see one activity at one time, but then you see another activity at a different time. So at the end, you have a sequence of activities or a sequence of observations. And then you want to see whether that is a hacking activity or not. So that is the anomaly detection. And sentiment analysis is another application. So one problem is like this: given a sequence of text, such as a review or a tweet, predict whether sentiment of the text is positive or negative. And so that is the sentiment analysis. So text is a good example of sequence because the word in the text, so their order is important. So a text is a sequence. And another example is the sign language understanding. So we use hand to communicate, and then the sequence of the hand gesture makes the difference. So the gesture sequence that is the sequence. The order makes a difference. So these are the possible applications of sequence similarity. And so in the case of the DNA sequence classification, so we are presented with such sequences, and then we want to tell whether this sequence is a coding region or not. So we are given some examples, and then we are supposed to build a model so that we can predict for any DNA sequence. So we are going to practice on this one later on. So this is one practice we are going to go through later on. And in terms of evaluation, so I have carried out an evaluation of the ACS similarity using the Australian Sign Language. So the Australian Sign Language, that is data sets available from the UCI data repository. And the original sign language is like this. It's like this. So every line here is a data instance. So these are the hand. These are the L and H represents hand gestures. So we have a sequence of hand gestures, and this sequence represents happy. And another sequence of hand gestures that represents angry, but angry has different representations. So each line represents as a sequence of hand gestures, and they are assigned different outcomes. So we have, that Australian Sign Language dataset consists of quite a lot of such sequences, and we are supposed to predict the outcome from the sequences, from a given sequence. And you can see that these sequences have different length, and so it is difficult to use the many machine learning algorithms because many machine learning algorithms require all data instances to be of the same length. And so for this problem, and we can use sequence similarity to complete. And so for example, we can use the k-nearest neighbor equipped with the ACS similarity. So given the data sets like this, I'm only showing you a very small sample of the complete data set. And here I want to show you six sequences. So given this data set, and if you want to predict a sequence, and all you need to do is to compare your sequence with each and every sequence in the data set, and we calculate the similarities, and then we can select the most similar sequence, and then we can classify the given sequence by the outcome of the most similar sequence. So that is the nearest neighbor classifier if the k value is 1. And if you want to increase the k value to 3, for example, then you need to identify the three most similar sequences, and then you carry out the majority voting. Then you classify your given sequence by the majority of your most similar sequences. So you can see in this process, the sequence similarity plays an important role. And this approach doesn't require all sequences to be of the same length. So it is quite useful. It is quite useful as well. So I have done an evaluation, and this is the result. So this is a summary of the result. So in this table, so I have evaluated the number of similarity measures. So this one is the ACS similarity, but equipped with the VHGK. So equipped with the VHGK. Then what is VHGK? Let's take a look at this one. The VHGK, that stands for this. So this paper. So this is a classical paper on the sequence similarity. So this was published in, I think it is the 2010, or 20. I think it is 2005, something like that. So that is a method of extending a similarity measure, because the similarity measure is defined for sequence of symbols. So there is an important operation to compare whether two symbols are equal or not. But if you apply the sequence similarity to numerical sequences, then the comparing equality of two numbers is sometimes problematic. So we need to extend the sequence similarity by from the equality comparison to a different operation. So the VHGK extend the equality comparison to calculating the difference between two numerical values, and then compare this difference against the threshold. So we set a threshold in the first place, then we compare, we check whether the difference is smaller than the threshold or not. If it is smaller than the threshold, then we regard the two values as being equal. So they are the first to introduce the threshold. So that is one way of extending a similarity measure. And so the second one is the LCS, that is the longest common subsequence. So that is another sequence similarity measure. So this measure has been there for quite a long time. That is the longest common subsequence. So this similarity measures the similarity of two sequences by calculating the longest common subsequences between the two given sequences. And then it uses the length of this longest common subsequence as an indication of the similarity of two sequences. You can see the longer this sequence, and then the more similar the given two sequences should be like. So that is the longest common subsequence similarity. And again, this similarity has the same problem. There is the equality operation in it. So if you want to apply this algorithm to a sequence of numbers, you need to extend it. And again, the threshold is used. A threshold is used to extend this. So that is the LCS VHGK. And the third one is the ACS similarity, but it is extended by the Euclidean distance. Euclidean distance. So that is a combination of the ACS and the Euclidean distance. So this is a combination of LCS with the Euclidean distance. This one is the ACS, but extended by the NCM. NCM is the similarity measure we discussed yesterday. That is the neighborhood counting metric. And this one is the LCS extended by NCM. So I evaluated 6 similarity measures in the context of the k-nearest neighbor classifier. So I vary the k value from 1 right to 19, and I run the k-nearest classifier. And these are the results. These are the results. And here clearly you can see the best result should be this one. You have you can see 100% for all k values. So that corresponds to the ACS similarity and equipped with the NCM similarity. And so the interesting thing is the accuracy doesn't change much as you vary the k value. So that is a very interesting and very important and the property because for the k-nearest classifier, a problem or a challenge is the choice of the k value. The choice. So to use it, you have to fix a k value. So whether you use a value of 1 or 10 or 20, so that is a big decision you have to make. But in the case of the ACS plus NCM, you don't need to care about this one because the performance doesn't change very much. So that is the first table. And then the second table is like this, the second table. And again, we evaluated the 6 algorithm, and then we vary the k value in the same range, but the data set is different. The data set is different. And so for the first table, the data set is the Australian Sign Language. That is a sample of the data. It only look at the 2 classes, com and the girl. Only look at two classes of the Australian Sign Language. But in the second table, the data set is the complete Australian Sign Language. And so that is the result. So you can see that the best result is clearly this one. It's clearly this one and this one. And interestingly, so the accuracy remains the same irrespective of your k values. And so that is an interesting property. But it is not the best for all the k values. And for example, when k is 1, the best value is this one, is the LCS extended by the NCM similarity. But the interesting property is the accuracy remains the same irrespective of the k value. So although the LCS give you the best result for 1, but the accuracy decreases. Accuracy decreases as the K increases. So that is the result of one evaluation. And there are limitations of the original ACS algorithm. So the one limitation is the repeating versus non-repeating. And so in the examples I gave earlier, so there's no repetition. So there's no symbols repeated multiple times. So what if there are repeated symbols? If there are repeated symbols, you can still apply the ACS algorithms, but the result will have a different meaning. So so there would be some repeated subsequences. Although the subsequences are obtained in different paths for multiple times, but they will be counted. They will be counted more than once. And if you are only interested in the distinct subsequences, and then the previous two algorithms will not give you the correct result. If you are only interested in the number of distinct subsequences, then the previous algorithms does not give you correct answer. So that is one limitation. And another limitation is for multidimensional sequences, multidimensional sequences, the previous algorithms works only for one-dimensional sequences, but it has since been generalized to multidimensional sequences. And we have already generalized the previous algorithms when there are repeating symbols. So we have generalizations as well. So another limitation is the situation when there are three sequences or more. So the previous two algorithms only work if you have two sequences to compare. And what if you want to compare three sequences to see how these three sequences are similar to each other? And what about if you have the 4 or 5, and the previous two algorithms do not work for 3 or more sequences, and we have to generalize them so that they work in this case. Now you may wonder, what is the meaning of such a measure when there are 3 or more sequences? Say, for example, if you have 100 sequences. So what is the meaning of such measure? So such a measure would measure the consensus among these sequences. So the one example is the voting. And many people vote for example, in the general election. So in some voting systems, so you need to write down, you need to select, you need to vote for a number of candidates, and you even need to put them in rank order to say which one is your first preference and which one is your second and third preferences. So so you can imagine there are hundreds of thousands of such preference sequences. and then you measure their similarity to generate consensus. So the meaning of, in this case, would be a consensus measuring. Then how these algorithms are generalized to deal with to address those limitations. So we have done further work to generalize them. So in the case of the repeating symbols, the limitation. So we have this theorem. So this theorem is published in this paper. Let me see. This one. And no, let me see. 3. I think this is wrong. This is wrong because the number 3 sequence, that is for graph. I think I must have entered the wrong reference key. It should be in one of these papers. Okay. So this theorem says that given 2 sequences like this, but they must be finite, and there should be non-empty strings from an alphabet A, and there could be repeating symbols in them. And then we introduce some notions, the L notion. So for a sequence X and for a given symbol sigma, so this L value represents the last and the max index of the symbol in X, such that the symbol is equal to sigma. So this value actually index the last position in the sequence that this symbol is present. So that is the meaning of this value. So this value is set to 0 if the symbol doesn't appear in the given sequence X. And then there are some special L values. And the value L for X is defined in this way. And it's defined in this way. So the XM, so this is the last symbol in the sequence X, and the X to the power of n minus 1. So this is the sequence X with the last symbol taken out. So that is a sequence. So this means that the LX. So this means we need to use the last symbol as the sigma value, and then we need to identify so the last occurrence of this symbol in this sequence. So that is the meaning of the LX, and the LY is defined in this way. So we take the last symbol from the X, and then we go through the Y sequence, and then the last occurrence of this symbol, its index is noted down, and then that is LY. So that is the meaning of LY. So on the basis of this, we can work out a recursive relation. So that is again a dynamic programming dynamic programming algorithm. And okay, so this quantity is calculated in two cases. And if the last symbol, if the last symbol of the two sequences are equal, then we can calculate this quantity in this way. And otherwise we calculate this quantity in this way. So the first line is like this. So imagine in the matrix we have seen earlier on. So we use the matrix to calculate the ACS value. And for any entry, we need to look to the top left-hand corner. We have three values to look out for. So this is one of the values. And this is again one of the values. And this is one of the values as well. And so these values are identified by the Ly and Lx. So it's pretty much dependent on where the last occurrence of the current symbol actually appeared. So this is the Lx and Ly, and I think it is better I illustrate it by examples rather than going through this equation. Okay, so that is how we calculate this quantity when the last symbols are not equal in the two sequences. Now let's try to understand this algorithm through this example. Okay, now we consider two sequences. X is like this: AB, ABA, CBCA, and clearly some symbols are repeated. A has appeared 3 times, B 2 times, and C 2 times. And the BCA and clearly B appeared 2 times. And we can apply the original algorithms, the original ACS algorithm, dynamic programming algorithms, and to work out the number of the common subsequences. But some subsequences will be counted more than once. I'll give you one example. Let's look at AB, and clear the AB is a common subsequence. AB appear here, but AB also appear here. Okay, AB appear here how many times? This is AB, this is 1 time, and then this is another time. 1 A here and the B come from here. So that is the second occurrence of the AB. And then the third occurrence is this one. A is from here, but B is from here. So the AB subsequence has 3 separate occurrences in this sequence. But AB has only 1 occurrence in this sequence. So as a result, the AB subsequence as a common subsequence should be counted 3 times rather than just once. But if you want to count only the distinct subsequences, and then you have to use the previous algorithm. And that means that for AB, you only want to count once rather than 3 times. So that is what I mean by counting distinct subsequences. So a subsequence is only counted once. But the question is, which subsequence do you want to count? Which one do you want to count? And to do so, and for A, you need to count this one. You need to count this, and for the B, you need to count this. So this is the occurrence, and this is the last occurrence of AB in this sequence. So you want to count this. So you don't want to count this. So you need to count this AB rather than this AB. And similarly, so the last AB occurrence is this one. So you need to record the last A and the last B. And so that one, and in this case, the last occurrence of B in that order should be this. And the last occurrence of A, and the A in this order is this one. Okay. So and to do so, we need the support of this matrix. We need the support of this matrix. And so this matrix is for one sequence for Y, and this is the matrix for X. And on these columns corresponds to the symbols A, B, C, because we only have 3 symbols. So we need 1 column for each symbol. And then the Y has how many? The Y has 4 symbols. So we have 5 rows plus the empty sequence row. And in the case of this this matrix, so this is for X. So X has 7 symbols, and plus the empty sequence, we have 8 rows here. And the meaning of this row, I will explain only one. Let's look at this column. And so this column, so for the symbol of A, so here we are looking at the sequence of the first two symbols, and the first two symbols should be AB. So, and in this sequence, A and the position of A, the last position of A is 1. Okay, and then in the sequence of AB, and the last appearance of symbol B is in the second position. So we have the value of 2. And now let's take a look at this one for the sequence of Y, which is this. And we are looking at the first 3 symbols. So the first 3 symbols would correspond to the sequence of BCA. And then the last occurrence of A in that sequence is in position 3. And the last occurrence of the symbol B in that sequence is in the position of 1. And the last occurrence of C in that sequence is in position 2. So that is the meaning of this the matrix. And on the basis of that, we can work out this matrix on the right hand side, on the rightmost side. So that is similar to the dynamic programming algorithm we have shown earlier on. So I'm not going to repeat it. So just look at one case. Look at one case. And so for every entry in this matrix, and then we need to calculate this value according to the previous. So the previous, the top left-hand side values. So the value of every entry is dependent only on its top right-hand corner. So I will skip the calculation of this matrix. So let's move on to the next one. So the previous algorithms can be generalized to work on multidimensional sequences. So, and the result is presented in this theorem. So this one is published in an unknown paper. So that is because this work has not been published yet. So in this theorem, actually this is quite a beautiful result, quite a beautiful one. So the given two multidimensional strings or sequence. So here I take the strings to be identical, a synonym for sequence. Two multidimensional sequence of length m and n respectively, without repeat the symbols. And then the quantity, the phi of m and n, so that is the number of, that is the count of the distinct subsequences. So this quantity can be calculated by only one formula rather than two formulas. Remember, in the previous cases, we have, in the previous algorithms, we have two cases. So when the two symbols are equal or not equal, so they should be calculated differently. But in this theorem, we only need one formula to calculate this quantity. So the first part is the same as before, and this is quite similar. So this is the same, and this is quite familiar as well. But here, this is different. So we need to multiply this quantity by this one. And here we have the s, xm, and xy. So what is the meaning of this? So this one is a similarity, but it is a normalized similarity. It is normalized to the interval of 0 to 1. So that is a quantity in that interval. And so that is a similarity measure for the two values. So these two values, xm and xn, so they are not symbols any longer because we are talking about multidimensional strings. So at any one position, it is not a symbol any longer. It becomes a vector. So given that it is a vector, we can talk about the similarity of two vectors. Okay, so that is one generalization. So this theorem can be specialized to the case where the two sequences are sequences of individual symbols. And then we end up with this case, end up with this. So this becomes identical to the one we have already seen earlier on. So so we can see clearly that this theorem is indeed a generalization of the dynamic programming algorithm we have discussed earlier on. So that is a beautiful generalization. So this example illustrates that generalization. And so again, we have two sequences, A, B, C, D, and the ADC. And so clearly their common neighborhoods or their common subsequences are the following. And the epsilon, this represents the empty sequence. So when the empty sequence counts as one common subsequence, so that is one common subsequence. So are A, C, D, because A, C, D all appear in both sequences. And then for two long subsequences, we have AC and AD. So altogether, we have 6 common subsequences. And we can follow the previous theorem. We can complete this grid according to the theorem, that in the end we will end up with this number, and this number represents. So this number represents the number of common subsequences between this sequence and this sequence. So that is a quite beautiful, beautiful algorithm. And it has been generalized. So your sequences could be a sequence of vectors. So that is quite beautiful. Now, as I mentioned earlier, another limitation is the case when there are 3 or more sequences. And this has been addressed in this theorem. So this theorem tells us that when we have 3 or more sequences, and we can still calculate the number of common subsequences of all of these sequences. So this work is published in paper 5. You see, paper 5 is this one. Yeah. So the paper is titled Concordance and Consensus. So that is because we have a lot of sequences to measure. So when there are more than 2 sequences, so the similarity concept becomes consensus or concordance. So here I only quote one theorem from that paper. So we consider three strings or sequences. So we have 3 strings, and we assume that they have no repeating characters. So this assumption is okay in some applications. For example, in the case of preference-based voting, so we need to write down our preferences. So every candidate should appear only once, a maximum of once. So we cannot write a candidate multiple times in our voting paper. So this assumption is true in this particular application. So the number, that magic number, that is the number of common subsequences, can be calculated in this way. So we identify a few cases, and if these symbols are equal, then we can calculate this number in this way. And all we need to do is to look up to the top left-hand side cell right on top of us, and then we double that number. And then, but if the xm is not equal to yn, then we keep the k remaining, and then we calculate this quantity in this way. And here you can see that the k remains the same. Okay, when this is the case, we only deal with x and z sequences, and then we keep the n unchanged, and then we calculate this quantity in this way. And here you can see n remains constant. And in the third case, we need to keep m constant, but we vary n and k. So we calculate this quantity in 4 cases. And then we have more general cases, so that will be dealt with in a different way. So that is too detailed for this presentation, so I will skip it. And so we have done other generalizations of the sequence counting algorithms. So that includes to count distinct subsequences in the string, to count distinct subsequences with a length of at least k, and distinct common subsequences of 2 strings, and to count distinct subsequences with a given minimum spans, and the matching subsequences as weighting of sequences. So this means we can apply weighting to the different subsequences. And so these cases are dealt with in one paper, that is paper 2. So that is published in the theoretical computer science. So that is the first joint paper I had with Sees, so Elsinger. So since that paper, we have published a number of joint papers. So in this direction, so that is on the neighborhood counting direction of research. We have published quite a few papers. Okay, so the spell sequence is another case. So the spell sequence is like this. So some sequences like this. So a symbol runs multiple times consecutively. So this occurrence of the sequence B runs 3 times, and this sequence runs 2 times, and the symbol M runs 4 times in the spell. So that is a special case, and this case is dealt with in that paper, number 4. That is versatile string kernels, and so that is done through dynamic programming algorithm. Okay, so in summary, so we have so for this part, for the neighborhood counting for sequences in this part, so we have demonstrated how a generic similarity can be specialized for sequence data. So the all common subsequences. So this measure, ACN's measure, is conceptually novel and practically usable as well, due to dynamic programming, because we have efficient algorithms to calculate this number. And the ACS has been evaluated, and it displays stable and competitive performance in classification. So I have shown you the evaluation result. And the ACS has been extended for multidimensional numerical sequences with or without repeating symbols. and the ACS can be calculated either through dynamic programming algorithms or through the grid algorithm. So I think I'm going to have a break. Let's take a half an hour break. Let's see what time is it now. It is almost 11 o'clock in my place. And so we are going to have a half an hour break. Let's resume in half an hour's time. Okay. I will see you again shortly.
Hello, Hui Wang. चले गए
किसी कोई नहीं चढ़े ऐसा जो म्यूट किया है
Hello, Hui Wong. Hello.
Hello,
How are
can you
you?
hear me now?
Yes, yes. We can hear you and we can see the screen as well. You can
Okay,
start.
can we make a restart now?
Yes, 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 yes.
Okay, welcome back and good afternoon. Let's continue. Today's workshop. Let me try to switch to full screen. Let me see. Yeah. Okay, so we have finished the sequence part, and now we're going to move on to the last topic, or the last main topic, which is for the graph. And so this is the neighborhood counting similarity for graph. So it is the specialization of the neighborhood counting similarity for graph. Now this is the outline for this part, and this is pretty much the same as before. The motivation, the concept, and the algorithm, because the similarity, how to count the similarity is quite important. I'm going to show some examples as well, and there are other extensions. Okay, before we talk about the motivation, I think a little bit background about the network analysis would be useful. So in common terms, we say network, but in academic terms, we say graphs. So networks are everywhere nowadays in modern time, and the Twitter, the LinkedIn, the Facebooks. So these social networks are pretty common, and it is now in our daily lives. And the science and citation, the bioinformatics and images, where the graph analysis can be used, and to analyze network for different purposes. So we can analyze network for different purposes. For example, we can try to find communities in network, and we can try to understand the behaviors which are presented as graphs. And so these analyses are typically done by way of classification or clustering. And in these, the operations, so in this way of analysis, a key operation is to compare networks, And the network comparison is typically done via similarity. So one example is if you have a large network, so you can compare one part of the network with another part in order to find some insight into the underlying dynamics of the network. But alternatively, you can also compare the network or the graph at one time with the graph at a different time. So that is the longitudinal, the network comparison, or the cross-sectional network comparison. So, and for these comparisons, and the similarity played an important role. And so the graph similarity underlines these analyses. So the graph similarity measures the degree to which two graphs, or could be more graphs, are the same. So this can be achieved by graph matching or the graph transformation. So in the case of graph matching, we are actually measuring the degree of matching between two graphs or a set of graphs. And in the case of graph transformation, so we can measure the effort in transforming one graph into another one. But obviously there are many different ways of transforming one graph into another one. So people typically measure the minimum effort that is required to transform one graph to another one. So there is already an extensive literature on the problem in graph similarity in various fields, not just in computer science. So and there are well-known solutions for the graph similarity measurement, but all need complex algorithms. So here are some examples. The graph edit, for example. So that is to measure the minimum effort that is required to edit one graph into another one. And the graph kernel, that is essentially to break down large graphs into smaller ones. And the maximum subgraph, and that is another well-known example. So this is quite comparable to the longest subsequence similarity, as we mentioned earlier. And all of these need complex algorithms. And the algorithms are so complex that it takes a long time to implement them. I would say it takes days rather than hours to implement these complex algorithms. And obviously better solutions would be desirable and always desirable. Better solution in the sense of efficiency and effectiveness. So when I first look at the graph edit distance, so I was actually surprised how difficult it is to edit, to implement that algorithm. So I have the feeling that these algorithms are very complex. And I asked myself the question, is there simpler algorithms? So I have the question before I started to look at specialized neighborhood counting similarity to graph. Okay, so that was the background. And the motivation for this include the simplification of graph similarity, and obviously the specialization of the neighborhood counting similarity to graph data. This is another major motivation. So once you can measure the neighborhood counting for graph, then you can calculate or you can estimate probabilities in graph data space. And so to specialize neighborhood counting for graph, and we need to go through the same process as before. So we need to precisely define the data space and the neighborhood space. So the given a set of nodes and a set of edges, we can construct different kinds of graphs. So all graphs that can be constructed from the given nodes and edges would be defined as our data space. If we are given a different set of nodes and edges, then we will have a different data space. And a neighborhood can be of different types in the case of graph. And for example, a neighborhood can be a subgraph, as we saw earlier for the sequence case. A neighborhood can be a subgraph, but the neighborhood can also be a path. And so when I was looking at this problem, I tried to I started with a subgraph as the neighborhood, but this turns out to be quite complicated. So at the time, I wasn't able to find an efficient algorithm to do the neighborhood counting for graphs based on subgraphs. So then I turn to look at a more simpler case, which is to interpret neighborhood as a path. And then the path is simply that is a path from one node to another one. And given the graph, and the number of different paths is certainly fixed. So that is what I chose. So as a result, the neighborhood space in this line of work, or in this specific research work, is the set of all paths. So given the set of nodes and the set of edges. And as a result, the neighborhood counting for graph is the count of common paths. So this means that if you want to measure the similarity, then you can use an algorithm to count the common path between two given graphs, or even more graphs. You can count how many paths that they share between them. So that is the concept. And based on that interpretation of data space and neighborhood space, and so I have collaborated with my colleague, with my collaborator, Professor Cis Elsinger, and we published one paper on this. So that is kernels for cyclic digraphs. So that means the graphs are cyclic. There are no cycles in the graph, and it is directed graph. And so this paper was published back in 2012. And a quick overview of the solution before we turn to look at the detail. So the solution is like this. So we need to represent the graph in some way. And here we chose to represent the graph by adjacency matrices. So graph can be represented in different ways, but we use this representation. And then we can count path in a single graph through the adjacency matrix multiplication. So we show that, and the path counting can be achieved by the simple adjacency matrix multiplication. So you begin with an adjacency matrix, you multiply the matrix a number of times, and then you will end up with a matrix, and then that matrix will contain information for the path count. So that is quite beautiful. And to count common path, the common path between two graphs, we begin with a common adjacency matrix, and then we do the matrix multiplication operation, and we multiply common adjacency matrix a number of times, and in the end we will end up with this magic number, which is the common path between two graphs. So that was an overview of the solution. Now let's take a look at some detail. And the graphs can be represented in different ways. And typically a graph is represented as a drawing like this. So on the screen, you can see a graph. You can see a graph. We have a number of nodes. There are edges, there are links between them, and the links have arrows. So that is a diagram or directed graph. And here, so that is one way of representing a graph. And a graph can also be represented as a tuple, just like this, we define the graph as a tuple consisting of V and E, and V is typically the nodes, and E is typically a set of edges. But interestingly, the graph can also be represented as adjacency matrix. So this is one matrix representation of the same graph, and there are 4 nodes. So the adjacency matrix will be 4 by 4. So every element in the adjacency matrix has a value, and that value indicates whether there is an edge between the 2 nodes. And so the entries are defined in this way. So an entry is 1 if there is an edge between the 2 nodes, and 0 otherwise. So look at this one. So at the position 2, 1, there is a value of 1. So there should be a link from node 2 to node 1, and you can go back to the graph, and there is indeed an arrow from V2 to V1. So that is the adjacency matrix representation. And the meaning of adjacency matrix, and we know the meaning of an individual entry in this matrix. So that indicates whether there is an edge in the graph. So we can call this edge as a one path, that is a one path or one length path, because the path has length 1. And if we add up those numbers, that should give us the number of all one length path. And in this case, we have 5. We add up those numbers, we have 5. So that means there should be 5 edges or one length path in this graph. Now you might want to ask yourself, what if the matrix is multiplied? If we multiply this matrix, do we get the n path, for example? That is the n length path. So we will have to see. Let's move on. Okay, to answer that question, let's multiply the adjacent matrix to see what we get. And we begin with a matrix for this graph. So now this graph is different to the previous one. In the previous one, we have 4 nodes, but in here we have 5 nodes, and that is the adjacent matrix for this graph. And we denote it by a to the power of 1. Now we multiply this adjacent matrix, then we end up with this. So that we apply the matrix operation. Let's take a look at this one. This value at the position of 3, 2, we have a value of 2. And that is obtained by multiplying this row by this row. So you can see that 1, 1, that give us 1, and then 1 and 1, that give us another 1, and the rest would be 0. So we end up with a value of 2. Then we keep multiplying, then we end up with this. That is a to the power of 3. That is obtained by multiplying the left-hand side matrix by the top matrix. And that we end up with this. So at this position, we have a value of 2. Then what is the meaning of it? That is 3 and 5. 3 and 5. We multiply this row by this column. By this column. No, we multiply this one, by this column. You can see that, so this one meet this one, and then this one meet this one. So we end up with a 2. So that is the multiplication. And in general, we have this. In general, we can do it in this way. And due to the matrix associativity, then this multiplication can be done in different ways. We can do it in this way. We take this row and then multiply it by this row, by this column. And so that will give us a value of 2 as well, because this 2 meets this 1 that give us a value of 2. So that is the matrix multiplication. And we can keep going on. We can keep multiplying this matrix by the original matrix. So that will obtain a matrix full of zeros. Now we can give it a try. We take this column and then we multiply it by this column. We take this row and multiply by this column. Then that will give us a value of 0, because there's no non-zero value at this position. So if we keep multiplying, we will end up with all 0 matrix. So there's no need to go any further. So that is how we do the adjacent matrix multiplication. Then, what is the meaning? What is the meaning of the adjacent matrix after we multiply it? Let's take a look. We know that for the a to the power of 1, that contains one long path. And then if we add them up, add the value up, then we are counting the one long path. And we multiply the adjacent matrix together. So that will give us a different matrix. That means we are counting 2 long paths. And to understand it, let's take a closer look at the values in this matrix. So this matrix is represented in this way. So this value can be expressed in this way. So that is how we do the calculation. And here, if you look at the red index, so they must be the same. So if at one position, at 1k position, and both a to the power of 1 and a to the power of 1, if both values are not 0, so that means there must be a path, a 1 length path from I to k, and there must be a 1 length path from node k to node j. And as a result, that will give us a 2 length path from I to j. So that is why we say that multiplying the 2 adjacent matrix amounts to counting 2 long paths. And generalizing this idea, so this matrix is actually to count k long paths. So that is the meaning of multiplying adjacent matrices. Okay, now let's have a closer look at one general case. So in general, we have a matrix a to the power of k, and the elements in this matrix has this meaning. So a to the power of k for I and j. So that means the number of distinct k long paths from vi to vj. Okay, and if we add up all these numbers, we will end up with the total number of k long paths based on the previous analysis. Now, so this is the number of paths for this length. If we vary this k value, then we should be able to get the list of all paths in a given graph. And so if we vary the k value and then we put these numbers down, then we get the total number of distinct paths in a given graph. So we can do the path counting simply by multiplying adjacent matrices. Now, to summarize the previous discussion, now we have this. We need to calculate the adjacency matrix for a given graph. So that is p to the power of 1, and then we represent it by p to the power of 1. Then we need to keep going. We need to multiply this adjacent matrix by itself. And then we have two matrices. Then we add them up. Add the two matrices up. Then we represent it by p to the power of 2. And in general, we have this. P to the power of n is defined by simply adding up those individual matrices. So we can keep going on until infinity. But at certain points, there's no need to continue going any further because the matrix will become empty. It is full of zeros, and there's no need to go any further. So at that point, we will end up with this case. So n to the power of infinity. That means that is already the end. That is saturated, and there's no point in going any further from that point. So we call it the all-path matrix. The all-path matrix. So that should include all path information. Now, having defined the P matrix in this way, then the meaning of the entries is like this. So if an entry is greater, so the entry should be greater or equal than 0. So that represents the number of the I to j path at most n long. So it could be one long path. It could be 2 long or 3 long paths. And so from this, we don't know whether the path is a 1 long path or 2 long path. So that is not what we need because we are interested in the total number in this case. Okay, and so p to the power of infinity for I and j. So this should be greater or equal than 0. So that means the number of paths of any length. There's no restriction on the length. So that is the meaning of this all-path matrix. And for this matrix, when we add up the numbers in that matrix, we will end up with a number. It is the total number of paths in G. So that is the meaning of this matrix. Now let's look at a concrete example. So we begin this graph, and then we represent it as an adjacent matrix. Then we follow the previous procedure, and we calculated that the all path matrix, p to the power of infinity. So that is actually like this: a to the power of 1 plus a2 and a3. That will end up with such a matrix. And now let's take a look at some entries to see whether the entries actually means the number of paths. Let's take a look at this one, the 3, 2, that is row 3, column 2, that is a number of 3. Do we have 3 paths from V3 to V2? V3 to V2. And how many paths do we have? We have 1 path, which is 1 long path. And we have another one, 2 long, V3, V1, and V2. That is a 2 long path. So we have 2 paths now. And the third one should be like this, from V3 to V4, and then back to V2. So we have 3, we have another 2 length path. And do we have any other path from between V3 and V2? And I don't think so. So as a result, we have 3 paths from V3 to V2 in total. Okay, now let's take a look at this one, the 3, 5. We have 3, 5. Again, we have a value of 3. Do we have 3 paths from V3 to V5? V3 to V5. This is 1 path. This is another path. This is another path. Indeed, we have 3 paths from V3 to V5. So that is no problem. And look at this one. Look at this one. And the bottom row are all zeros. All zeros. Why is that the case? So that is because there's no edge leaving V5. So the V5, there's only 1 incoming arrow to V5. There's no outgoing arrow from V5. So as a result, so this row is 0, and that is correct. So the path counting in this way is indeed correct. So as a result, the total number of paths in this graph is 13. The 13. Let's do the calculation. So that is 7. That is 9. So that is 8. That is 10. 13. Yes. So it is 13 by this matrix, and we can enumerate all 13 paths in this way. So there's no problem. So that is an example. Now we can count all paths in one graph. How to count the common path between 2 graphs? How to do so? And this can be done. This can be done by common adjacency matrix. So previously we saw adjacent matrix, but that one is only for one graph. For one graph. And so if we want to count common path, we need to look at the common adjacent matrix. Now let's have a look at this one. Here we have 2 graphs, and we represent it by adjacent matrix like this. And this is the second adjacent matrix for the second graph. And their common adjacent matrix is this one. So that can be obtained. It can be obtained in this way. So that is how the entries are defined. So the entry is 1 if the both individual matrices have 1 at the same position, and it is 0 otherwise. Now here, let's take a look at the common adjacent matrix. We have only 2 ones. In this position, there is 1, so there must be 1 in both matrices at the same position, and you can see clearly that is the case. So there is a 1 here, and there is a 1 there in the same position. And for this one, so there is 1 in this matrix and 1 in that matrix in the same position. So that is the common adjacent matrix. So that is how we obtain the common adjacent matrix. And this corresponds to this subgraph. So this subgraph is obtained by deleting certain edges. So there should be one edge between V1 and V2, and there should be another edge between V2 and V5, So that is correct. So that is the common adjacent matrix. Now, having the common adjacent matrix, then how to count the common path? And now we can use the same magic. Do the matrix multiplication. So we begin with the initial common matrix. Then we multiply this matrix by itself. Then we end up with another matrix. Then we add up those individual matrices and their multiplications. We add them up. Then we get a P matrix. So we defined the P matrix before. So in this particular case, the P to the power of 2 for the common matrix is obtained in this way. So that is this matrix plus plus this one, and this gave us this matrix. So this is the P matrix. And we can keep going, but it doesn't change anymore. So that is the P to the power of infinity. Now let's take a closer look at this one. A closer look at this. And here we have one value. And so that corresponds to V1 to V5. V1 to V5. Yeah, there is indeed a path from V1 to V5. And there is a one from V1 to V2, V1 to V2. And there is a path from V2 to V5, V2 to V5. Indeed. And that should be all the path that we have. And as a result, and if we add up those numbers, we get 3. That 3 corresponds to the R2 path. So that is correct. So we put all the numbers together. That will give us the total number of the common path between the two graphs. So we apply the same procedure as before, but we begin with the common adjacent matrix. So instead of the individual adjacent matrix for a graph, we use the common adjacent matrix. So based on the analysis, and then we have these conclusions. So the common path counting is a measure of similarity. So for any function to qualify as a similarity measure, we need to look at two extreme cases: when two objects are identical, or when they are completely different. And then you can see whether this your function give you the right number. And so the two graphs are perfectly similar when they share all paths. So you can imagine that, and when two graphs share all the paths, so that means they are perfectly similar. They are essentially identical. So the two graphs are perfectly dissimilar when they share no path at all. So when two graphs share no common path, then they should be perfectly dissimilar. So as a result, so the common path counting is indeed a measure of similarity. And the more path they share, then the more similar graph they are. And so the hour graph similarity is then defined as the number of common paths, which is denoted by TGH. If we want to normalize the graph similarity, then we can do so because we know that this quantity is less than any of these numbers. So that is the total number of paths within graph G, and that is the total number of paths in graph H. So this is the total number of paths common to G and H. And clearly this number should be smaller than either of the two. So as a result, we can normalize graph similarity in this way. And so this value is divided by this, the product of the two and square root. And as a result, so this normalized similarity should be in the range between 0 and 1. So when it is 1, so that means the two graphs are maximally similar. They are essentially identical. So when this value is 0, so that means there's no commonality between the two at all. So they are not similar at all. And now let's take a look at an example to calculate the normalized similarity. Okay, and we have two graphs, and that is the common graph. And then applying that procedure, we can work out the total number of paths for this graph, and that is 13. And for the second graph, it is 14. And then there the common graph, and the number of common paths is 3. And as a result, the normalized graph similarity is like this. And so that is quite interesting number. Now, in terms of the algorithms to do so, and so we have outlined the procedure to calculate the P matrix, and the computing the P matrix directly has a complexity of the n to the power of 4. That is quite big number. That is quite a big number. Now, why this is an n to the power of 4? Let's go back to look at the P procedure. Now look at this one. So this one adjacent matrix. So the calculating this one has a complexity of the n squared, because that is how many number of values in this matrix. And then we need to do so how many times? 1, 2, 3, and 4. We need to do at least n times. Look at this. Okay, so that is the n squared, n cubed. And then for calculating this individual p to the power of n, we need to calculate. We need to do so n times. So as a result, the complexity of this p procedure should be n to the power of 4. That is n cubed times n plus a constant. So the complexity should be n to the power of 4. So that is very large, very large number. But fortunately, and the people in the past have already come up with the efficient solutions to such a problem. And so these two papers provided inspiration for us to design an efficient algorithm. So so in the same spirit of these the Floyd and Warshaw algorithms, and we have designed an algorithm to calculate the p, which has a complexity of n cubed. So this is the algorithm, and this algorithm is published in this paper. Yeah, the kernels for a cyclic diagram. Okay, we begin with a matrix, adjacent matrix. That should be a square matrix. And this matrix can be the adjacent matrix for an individual graph, but it can also be a common adjacent matrix for two graphs. Okay, we initialize P matrix by A, and then we have these loops. We have 4 loops, 4 nested loops, and for P from 1 to n, and for P from for I from 1 to n, for J from 1 to n, and then we just do this simple calculation. You can see this algorithm can't be simpler. But the complexity of this algorithm is n cubed because we have 3 nested loops. And so if A is the adjacency matrix for a single graph, then P gives the number of all paths in this graph. But if A is the common adjacency matrix of 2 or more graphs, then P gives the number of all common paths. So you can see the algorithm can't be simpler. So this algorithm can be implemented in how much time? I think this algorithm can be implemented in minutes, or at most in hours. So that is a big contrast to many of the existing graph similarity algorithms. Okay, some quick examples. So that is a graph. And then if you are asked to calculate how many graphs are there in this graph, and you can calculate by yourself because this is a simple graph, so it shouldn't be too difficult to identify all the paths. But what about this? you have a complicated path, a graph. If you are to identify all the path in this graph, can you do this in minutes? Not to mention in seconds. It is not so easy. Not so easy. But this can be done quickly through that simple algorithm. Okay, let's have a quick review of path counting. And the calculation of rho, that is the normalized graph similarity, is quite fast. At least the algorithm looks quite simple, although the complexity is NQ, but that is still fast for graph comparison. And the easy interpretation and the meaning of that number is quite clear. So the rho means the fraction of path that is common. And the rho can be easily generalized to more than 2 graphs. So if you have n graphs, then all you need to do is to calculate the number of common paths. And then you can divide it by this quantity. Then you end up with a measure of the similarity between those n graphs. So that can be easily generalized. But the rho is narrow-minded. So I use the quotation, it is narrow-minded, because the meaning is not clear without going to the next slides. It is narrow-minded in this sense. Now let's take a look at these 2 graphs. So these 2 graphs they look quite similar. They should be quite similar in the sense that the V1, V2, and V3 are all connected to V4 in both graphs. Look at this. V1 is connected to this. V2 is connected this. V3 is connected. And V1 is connected to V4, V2, and V3. And the only difference is, so V5 is not connected to any nodes in this case, but in this case, V5 is also connected to V4. So there is a lot of in common in between the 2 graphs. But if you use the previous algorithm to calculate similarity, then the rho value is quite small. It is quite small. And that is because there's only one path shared between the 2 graphs, which is V3 to V4. That is the only path shared between the 2. Now let's take a look at this one. From V to V4, there is a path. There is a path from V1 to V4. Yes, there is a path, but the path details are different. The path details are different. So that is the path detail. It goes from V1 to V3 and then V4. So this is V1 to V5, V3, and V4. There's only one additional node in this path. So as a result, we say that the path is restrictive or narrow-minded as a measure of similarity. That is because we use the concept of path. For 2 paths to be the same, we need to make sure that everything is the same. So that is quite restrictive. So as a result, we need a new concept, and our choice of the new concept is ticket. Okay, so this is our the new concept. We use ticket. Hello. Okay, so we use the ticket instead of path. So a ticket is simply a path with any number of nodes deleted from the path. So we only need the two end node. We can ignore all the nodes in between.
English में ना बताया ना
So that tell me, hello, are you speaking to me? Hello, do you want to speak to me? Okay.
عشان باكستان الإنجليش هذه شافة.
Okay. Okay, thank you. Okay, so a ticket is actually a contracted path in the sense that we only keep the end nodes and we can delete any nodes in between. Okay, and using the concept of ticket, then these two graphs, they have a lot in common. And you can see that we have a ticket from V1 and to V3, and then V1 to V4, and V2 to V3, V2 to V4, V3 to V4, and V1 to V4. That is another ticket. So you can see that we have a lot in common. So all of these are shared between the two graphs. Okay. And now the question is how to count the common tickets between two graphs. So that becomes an issue now. And before we move on to look at the algorithm, we need to discuss a few observations. Okay. The all paths of G are tickets too. So the path themselves, we are able to count path within the graph or between two graphs. And every path in the graph is a ticket. Okay, every path in the graph is a ticket. Okay, so if X is a ticket, then deleting any number of intermediate nodes from X will result in another ticket. So in the previous one, so here we have this ticket. We can delete the V3, then we end up with another ticket, which is this one. Okay, and then for this ticket, we can delete any intermediate node, then we end up with another ticket, which is 2, 3. Okay, so that is another observation. So if Vi and Vj and Vj and Vk are tickets, then by joining these up through Vj, we have another ticket, and we also have another ticket, Vij, Vi, Vj, and Vk. So these are our additional observations, and based on these observations, that we can present the path implied ticket, or to count the tickets. Okay, and we know this notion already. So that implies that is the matrix for all path matrix. And so we know the meaning of this. So that means the number of the path between I and j of any length So and then based on the previous observation, so that also means there is R number of the one length ticket. So if this value, if this value is R, then that also means there are R tickets between Vi and Vj, because every path is also a ticket. Okay, so we begin with this, and then we apply the same procedure. But here we introduce a new notion, which is E matrix. And so this is defined, the E to the power of 1 is defined as the P to the power of infinity. And we take it as one ticket matrix implied by all path matrix. And so that is to count all one long tickets. So this is similar to the adjacent matrix. Then we apply the same procedure. We multiply them. So that amounts to counting 2 long tickets. And in general, the n long tickets. And then we add the numbers up. That will give us, and they give us all tickets at most of this length, n long. So this process will end at the point when there's no change. So that is called the T to the power of infinity. And so that means the all ticket matrix of any length. So this is quite similar to the previous procedure for P. But here we begin with the P to the power of infinity based on the previous the observation. And then counting the common tickets is the same. We need to start with a common matrix. So that is how it is defined. And then we repeat the same procedure. We do the matrix multiplication. And in the end, we should end up with such a matrix for the common tickets. And then that will give us a count of all tickets, common tickets. Okay, let's take a look at this example. Take a look at this, and this is the example we use as the motivating example for the ticket. And now we have so this is based on the ticket calculation. So we have this for this graph. This is for the common part, and for the common part we have 7. And then for this matrix we have, that is 5, that is 6, 12, 13, and then 16, and this one should be 7. Yeah. So we know previously that if we use the path notion, we end up with such a similarity. But if we use the ticket instead of path, and their similarity becomes bigger. So this is 7, and then the denominator is like this. So the similarity value is 0.661. So that is closer to our perception. And so that is another concept to measure graph similarity. Okay, now to generalize at the conceptual level, we can the graphs can actually be represented as ticket vectors, or if you prefer, you can represent the graph by the path vectors. But the concept would apply in both cases. So we begin with the set of all nodes for your problem, and then we derive the set of all possible tickets. All possible tickets. But this number is found to be quite huge. It's quite huge. It's colossal. So if the number of nodes is 20, and then that space is massive. That is 10 to the power of 18. That's really, really colossal. But you don't have to work it out explicitly. You only have this one in your imagination. And then we can index these tickets in this way. So we can say which one is the first, which one is the second, because this is finite. So you should be able to put them in an order. And as a result, you can create a vector for a graph in this way. So the vector is like this: G1, G2, and Gn. And the value is defined in this way. So it is 1 if the path in that position is a ticket in this graph. So this means if it is 1, so this particular path ticket is indeed a ticket in G, then you give a value of 1 for that position in this vector. Otherwise, you give a value of 0. So that is how we can construct such a vector for any graph. And as a result, you can use vectors to represent any graph. So in the same way. So that is the ticket vectors. So as a result, the number of distinct tickets can be easily calculated through the vectors. And all you need to do is to do the inner product of the vectors. So this will give you the number of distinct tickets in graph G. And then you could do so for the other graph. And then the number of common tickets can be calculated by the inner product of two different vectors. And as a result, the normalized similarity between the two graphs can be calculated through vectors in this way. So the inner product of two vectors and then divided by the length of the two different the graphs. So that is essentially the cosine similarity between the two vectors, the vectors of G and H. So as a result, the normalized similarity measures the angle between the representing vectors. Okay, so the smaller the angle, the bigger the rho value. Okay, and now we can, so with that representation, we can easily define the similarity, and then from that similarity, we can also define a distance function that quite easily. So the distance function can be defined in this way. And so that is the vector representation, and that is the path or ticket count. So that is actually a Euclidean distance. And Euclidean distance can be calculated by subtracting the two vectors, and then you raise to the power of 2, and then you calculate square root. You do it that way. So that gives you precisely like this. So such a distance is actually the Euclidean distance in the vector space. And the meaning of this distance is pretty clear through this. It's pretty clear. So that is the number of non-common tickets in both graphs. So you add up these two numbers, but then you take away the common part. So that means the number of non-common tickets in both graphs. Okay, in summary for the graph section. So the graph similarity can be calculated easily through the elementary matrix operations. So we can easily calculate the graph similarity as well as distance. And there are clear interpretations for the similarity and the distance. And geographically, we have said that so the similarity measures the angle between the two vectors, but numerically, the similarity measures the fraction of shared the path of tickets, and the distance means the number of non-shared path or tickets. And so this similarity can be easily generalized to more than two graphs. So we have already explained this earlier. But the caveat is the theory here is for directed acyclic graph only. But even there is such a limitation. So there are still plenty of applications. And importantly, we have recently generalized the work to undirected graphs and the cyclic graph as well. So this work is done by my PhD students. Okay, now a recap of all the topics I have covered so far. And so I have covered the contextual probability and the neighborhood counting as a similarity kernel, and the specialization of the generic similarity for three types of data: multivariate, sequence, and the graph. So the contextual probability is a frequency probability. In the sense that we begin with a sample and then we calculate the frequency, and then taking into consideration the ordering relationship between within each dimension. Remember, we have shown a simple example on the two-dimensional grid. And so if every dimension is ordinal, then that means the squares, they have ordinal relationship. So when we calculate the frequency probability, then we have indeed taken into consideration that the ordering information. And the contextual probability can be estimated through neighborhood counting. So that is an interesting finding, and that connects probability and the neighborhood counting similarity. And remember, the contextual probability has a simple relationship with the probability that you are interested. And the contextual probability is secondary, and the probability you are interested in is primary. So one is defined by the other one, and then they enjoy a simple relationship. And so neighborhood counting is a generic similarity kernel. So it is generic in the sense that it can be applied to any type of data. And the similarity is governed by the axioms. And the kernel has the interesting property that the similarity can be broken down into the product of two values. And the neighborhood arises in different forms for different types of data. So we have seen, and in the case of the multivariate data, a neighborhood can be treated as the hyperrectangle in your multidimensional space. And in the case of sequence, a neighborhood can be regarded as subsequences. And in the case of graph, and the neighborhood can be taken to be the path or tickets. Now, in conclusion, and the applications. So I have presented the general methodology for probability estimation, as long as a general methodology for similarity measure. Then you may wonder, is there any application? Is there any application of these works? And clearly there are applications. So I would say that anywhere where similarity needs measured or probability needs estimated. So and then it can be applied to anywhere. For example, in machine learning, the similarity measures can be used in k-nearest neighbors, in the clustering algorithms such as k-means, or the k-space reasoning, or even in Gaussian mixture models where you need to measure distances. And we have already evaluated the similarity measures in k-nearest neighbor on public data sets. And recently, I have formalized the notion of subsumption and quantify the notion of the subsumption through another paper. So this is the new paper that is published in 2018. So it is called the quantifying sequential subsumption. So this is based on the neighborhood counting concept once again. So this is again jointly with my collaborator, C. Singer, and supported by my students. And so this and the sequence similarity that can be applied in time series analysis. And information retrieval as well, that is another possible application area. Now, I haven't mentioned the related work, and actually there are two pieces of work which are related to the contextual probability and the Dempsey-Schaffer theory of evidence. This is related to the contextual probability. And in Dempsey-Schaffer theory, we need a mass function. And the mass function is usually assumed given by expert. So the expert's beliefs are quantified through mass function. And the Dempsey-Schaffer rule of combination is widely used for example, in data fusion. But in reality, the mass function is difficult to obtain from expert. But the data is easy to collect, and the knowledge from expert is hard to elicit it. And in the same spirit of the contextual probability, we have done some work on deriving mass function from data systematically, rather than relying on mass function provided by expert. So that piece of work is relevant to the contextual probability. And another relevant work is the kernel method for probability estimation. So yesterday I showed you one slide to show how to estimate probability through kernel method. So we need to use a kernel function, and then we need to go through all the examples in the data set and measure the kernel similarity value. We add them up, and then we normalize it to become a probability. So in this sense, it is quite related to the contextual probability. So what is different between the kernel method and the contextual probability is the contextual probability is can estimate probability through neighborhood counting, and the neighborhood counting has very clear physical meaning. And when you use a kernel method to estimate probability, then the physical meaning isn't clear enough. And there are different kernel the functions to choose from, and every kernel function will correspond to different meaning. Will have different meaning. But precisely what is the meaning? What is the meaning? That is unclear. So that is the similarities between kernel and contextual and their differences. And in terms of the future work, and my current research interest is knowledge-based learning. And knowledge-based learning in the sense that we want to do the learning by taking into consideration the existing knowledge, and we represent existing knowledge, either propositional or first-order logic knowledge in the data space, and then we also have a lot of data, and then we want to extend the knowledge. We want to generalize the knowledge based on the data. So this is what I mean by knowledge-based learning. So this is my current research interest, and then my goal for this one is I want to represent the body of knowledge for a specific domain. For example, for the school mathematics, for the school history, for the school the language. So there is a body of knowledge, and I want to try to represent that body of knowledge through this means. And another future direction is the general artificial general intelligence. So that is something I am interested, but I haven't started working on this as yet. Okay, so that's and so that concludes my presentation for this workshop, and I have prepared some practices. So I prepared the four sheets of practice work. We have completed 2. I want to quickly go through one practice. So if I have time. And Professor Sadiq, do we still have some time to work on one practice? It is now, we have 7 minutes to go before the 6 o'clock. Okay, so that concludes my presentation. And we certainly can't complete all 4 practices. but there's one I want to quickly go through if I am allowed. And
Yes, you can, please.
okay, let me quickly, I think we should be able to do that. It is the NCM that I want to quickly go through. Let me see. Okay, this is, okay, let me move something from, okay. Okay, take a look at this one. Yesterday we discussed the NCM similarity, that is the neighborhood counting for multivariate data. And so I have implemented the NCM similarity, and it can be used in some way. Okay, let's run this from the very beginning. So I have already sent you this Jupyter notebook through the Zoom chat box. Okay, just quickly run through these. Okay, so this is the same, we have done it. Okay, so this is the NCM similarity for two arrays. So I implemented the NCM similarity because the sklearn or many deep learning programming is written in using the so-called the array programming. So it operates on arrays rather than on numbers. So I wrote this program to calculate similarity for two arrays. Okay, so I define this NCM. So the input includes one array and two arrays. Look at this one. The A, B, they are input arrays of shape MD and ND. So they should have the same dimensionality, the same same D, but different M or N. And the MN here, that means it is the mean of the domain. It is the minimum of the domain for each attribute. And the MX, that means it is the maximum value for every attribute. And the E, that is the quantization parameter. And so I want to calculate the NCM similarity between A and B. And you can see it is fairly simple, And somebody asked me this question yesterday offline. Why do we need to add one here and add one here? So this can be obtained. Let me think. So for this one, so this is part of the theorem. So this is theoretically derived, and I think I have no time to explain this. I just want to quickly run this algorithm and then see the result, and I will leave the rest. Let me okay, so this is where we are. Run it. Let me see. Okay. There should be some value here because the print has been executed. There must be something wrong. So Professor Sadiq, I think time is up, and there must be something wrong with the setting. You can see this one is not, it should print out some result because the distance are already calculated, and there should be, the result should be printed and should be displayed here. And I don't know why it doesn't show anything. And I have no time. I think probably there's no time to fix it. But anyway, I have already uploaded this notebook to the chat and the chat box, and then I have also written some comments. So if you are interested, then you can certainly take a look at this. And so this is to help you understand the NCM similarity. And another one I would like to show is, I just would like to point out is this. Let me see why this is the case. It seems to me there is something wrong on my laptop. You can see the files are not presented in the right way. So this is quite different. I probably need to restart my laptop. Okay, I think I will leave this one because in the other Jupyter notebook, I leave something as an exercise. So that is to implement the dynamic programming algorithm for calculating ACS. So if you are interested, you can try to implement the ACS algorithm in that notebook and then replace the default, the distance metric by the ACS similarity. And then you can repeat the sequence, the DNA sequence prediction and the experiment.
Thank
okay,
you.
So that is the exercise I said in that notebook. So if you are interested, you can certainly try this. And okay, I think that's all from me. And thank you very much. And it is a great pleasure to be able to speak in front of so many people and to speak at this forum.
Thank you.
I will hand it over to you.
Yes, we formally start the closing ceremony. So we are requested to all the participants to stay connected. I request for the recitation of the Holy Quran, Usama Ahmad Siddiqui.
أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم إذا جاء نصر الله والفتح ورأيت الناس يدخلون في دين الله أفواجا فسبح بحمد ربك واستغفر إنه كان توابا صدق الله العظيم.
Jazakallah. First of all, on behalf of the Comstech and IEEE Karachi section, I am really thankful to Honorable Vice Chancellor, University of Karachi, Professor Dr. Khalid Mahmood Iraqi Sahab, to be with us as a chief guest to be on the closing ceremony of the 2 days hands-on workshop on contextual probability, concept, implementation, and application that organized by Comstech Ministerial Standing Committee for Scientific and Technological Cooperation in collaboration with IEEE Educational Activities, Karachi section. I'm really honored and thankful to Professor Dr. Mohammad Iqbal Chaudhry, he's Coordinator General Comstech. Due to some urgent engagement in Islamabad, he cannot join us in this session. Yesterday, he is with us. We have Professor Dr. Bhavani Shankar Chaudhary with us as Chair IEEE Karachi section. I am really thankful to sir to be with us. We are part of this activity. Professor Hui Wong from Ulster University, UK, that delivered a workshop as a resource person. About 80 participants attended the workshop online for the 2 days, and 30 participants attended the workshop physically at Ali J Center. The workshop coordinated by Comstech and IEEE, a joint venture. Professor Hui Wong covered the concept of contextual probability, its relationship with the functional probability, and practices some real examples. Hui Wong emphasized the application of machine learning related to the different type of data sets. Hui Wong explained how contextual probability can be used for decision making and for general problem solving. Professor elaborated how neighborhood counting has been applied to multimedia data sequence and for the graph resulting in elegant similarity measures. Now I request Professor Dr. Bhavani Shankar Chaudhary to say a few words on behalf of IEEE Karachi section.
Thank you very much, Professor Dr. Sadiq Khan Saab. I'm highly grateful to Karachi University, Vice Chancellor Karachi University, and Comstech and Professor Dr. Iqbal Chaudhry for giving IEEE an opportunity for co-organizing such an event, which is highly beneficial for our students, graduates. That is the very important component of professional development. I attended some of the sessions yesterday and some today as well. So it's a great professional development contribution by the resource person. I think this is what we can achieve in due to this COVID situation. We are having such a good resource person contributing for transferring latest up-to-date knowledge on these emerging technologies. So on behalf of Karachi section, I am highly grateful for all the support, and really it is even credit goes to even this IEEE as well, that we are having collaborative event. That is what IEEE believe in the advancement of technology for society, and the Karachi University, Comstech, they are playing really pivotal role. I'm highly grateful for that, and I congratulate Dr. Sadiq Khan for organizing such a wonderful event with such a good participation, and I hope those who have attended, they will continue, keep in touch with the resource person to get maximum benefit. Thank you very much.
Thank you. Now I request Professor Hui Wong to say something about the workshop, about the participants.
Okay, so I would like to thank you, Professor Sadiq, for the kind invitation and for the excellent arrangement for this. So it is a great honor to give a presentation on this forum. So it is a privilege as well. This is my first time to give a presentation at this event. So I am so I hope, I do hope that people who attended this workshop will have benefited in some aspect. And so I hope this will be the start of a long-term collaboration. So I hope I will be able to collaborate with some of you in the future.
Thank you, Hui Wong. Inshallah, we will collaborate and continue the support in future as well for the research projects. Now, I request our worthy Vice Chancellor, Professor Dr. Khalid Mahmood Iraqi Sahab, to be here and for the closing address there. So I request Professor Dr. Khalid Mahmood Iraqi, Vice Chancellor, University of Karachi.
First of all, let me confess that the ComSet and IEEE Karachi division or the chapter, they have organized a two-day workshop in order to enhance the skills of the participant. As Dr. Sadiq told that there were around 80 participants virtually participated and 30 or 35 physically participated in this workshop. I think with the change in technology, there is a requirement, a regular requirement to have such workshop so that we can enhance the skills of the people who are engaged in different professions. We live in a century where technology has its utility, and the COVID-19 situation has established the fact that the societies can make progress if they use technology. If you're not using technology, then you cannot make a progress. The COVID-19 situation, particularly for universities, it was a big lesson that how we can have online education. Yes, there were problems and there are still problems in terms of connectivity, in terms of the skills, but this COVID situation, as per the research, is going to prolong for a longer period of time. And you have to live with this COVID-19. And if we have to live with the COVID-19, my advice to young generation and people who are engaged in profession, they have to believe in science. Unfortunately, I live in a society where we are in denial phase. ठीक है कि कोविड तो हमें कुछ नहीं करेगा, ठीक है, यकीन ही नहीं है कि कोविड-19 सिचुएशन हो सकती है, ठीक है। वो कहते थे कि जी ऐसे ही सुनने में आ रहा है, जब अपने रिश्तेदार मरने शुरू हो गए तो यकीन आना शुरू हो गया। ठीक है, सो मेरी हम्बल सबमिशन है लोगों के लिए कि दिस इज एन एज ऑफ टेक्नोलॉजी and we have to believe in science and we have to fulfill the prerequisite, and the prerequisite is you're supposed to have your knowledge, use your knowledge, enhance your skill, and then produce result. And I was very much impressed by the title of the workshop, and for me the last two terms, the last two words are very important. That is implementation and applications. Right? I am a student of public policy. My specialization is public policy, and we talk about policies are judged on the basis of results produced or impact in a society. And you cannot have impact without implementation and application. And I hope this workshop will provide you an opportunity to explore the different areas. Once you are in this field, you have to live in a constant search for knowledge and enhancing your skills. If you have the skills, then no one can stop you from making progress. I live in a society where still there is a requirement that we should have a proper electrician, a proper plumber, and a mechanic. ठीक है? जब किसी कार जो लोग बनाते हैं ना, मैंने देखा, I had a small car, तो जब उसे नट नहीं खोल रहा था ना, तो उसने हथौड़े से मार के खोल दिया. So, abhi bhi, if you have a problem with your refrigerator, if you have a problem with the home line appliances, it is difficult to find people with certain skills. So, my humble submission is, when we talk about the employment opportunity nahi hai, kaam karne ko nahi mil raha hai, it is because the lack of skills. If you have the skills, then you can survive, you can make progress, and you can achieve the target you can set. So आप सबको देख के मुझे बड़ी खुशी हुई कि शाम 6 बजे तक भी लोग यहाँ बैठे हुए हैं. ठीक है? So I am particularly thankful to Comstech, IEEE, LEJ, Dr. Nadeem साहब यहाँ पे होते हैं. He is a very dedicated person, and I must confess that you have a very strong team. We have organized this event in terms of coordinator Dr. Sadiq Ali Khan, Hina Siddiqui, and the people from Khazima Muazzam, program manager, and last but not the least, we must appreciate the resource persons. Without their contribution, no workshop has any meaning. So I am very particularly thankful to all the resource persons who were engaged in this workshop, providing their expertise and inputs to our participants. Thank you, ladies and gentlemen.
Thank you, sir. And really a great honor for me and for us, Honorable Vice Chancellor, to be here, to be a part of this occasion. And he always encouraging such kind of academic and activities that helpful in boosting the knowledge of the student, the research culture in the University of Karachi. And I'm really honored and thankful to Professor Dr. Muhammad Iqbal Chaudhry Saab and from Ms. Khazima from Comstech, and Dr. Hina, LEJ, Dr. Nadeem, to be here for their support and I'm really thankful to Professor Dr. Bhavani Shankar Chaudhary for their always encouraging for us. Due to his effort, the IEEE Karachi section is struggling day by day, and we boost the level of the IEEE Karachi section under his leadership. I'm really thankful to my dearest brother, Professor Wee Wong, to be a part of this workshop, and he accepted my request as a resource person, and he engaged himself for 2 days, deliver a very informative, knowledgeable talk related to some practical example with the very latest technology, that is machine learning, and how we apply that there. I'm always thankful to the technical team of LEJ, especially Fasi, Salman, and especially thankful to Malia and all the volunteers there. We have some small token of appreciation. First of all, I would like to this is a small token of appreciation from us for you. This is a certificate of appreciation for you. Now I request Vice Chancellor to be on the stage, sir, please. And Dr. Nadeem, please.
Good evening, everyone. Mohammad Salman Ghani for his IT support. Please clap for him. He was the person who was giving me the services. Mohammad Fasi. Thank you so much, sir. Mohammad Fasi. For the volunteers, Arsalan. Fatik. Hafsa Siddiqui. Mama Zafar. Fahim Ahmed. Ghulam Murtaza. Ubaid Ahmed. Ubaid Ahmed. Huma Hassan. Mohammad Naseem. Usama Ahmed Siddiqui. Khalid Khanzada. Saad Ansari. Muhammad Aslam. Muhammad Hamza. नेहा, नेहाल खान, डॉक्टर फौजिया, अबीरा, मोहम्मद हमजा, remaining participant can please make the line. Remaining.
बाकी आप लोग के जो है ना वो दे
ये देते जाओ। आप भी please देते जाओ। Kindly आप लोग यहाँ से लेते ही जाइए।
ये पास में
आप लोग प्लीज रिसीव कर लें, फिर मैं आपसे दे दूँगी। इनको दे देना। हाँ, अच्छा।
डॉक्टर आसिफ आप अपना
हाँ।
तो सिर्फ वो नाम डॉक्टर आसिफ प्लीज
Excuse me, ma'am. Hello. Excuse me, ma'am.
Last but not the least for me.
those who do not receive the certificate will receive electronically. And I request for a group photo be here, please. Thank you, Yvonne. Thanks to Professor Dr. Iqbal Chaudhary, Khalima, Dr. Hina, Dr. Bhavani Saab. Please.
आप प्लीज आ जाइए, नीचे सेटल डाउन हो जाइए और नहीं सर आप